Oh, goody. Okay, so this is what a boom arm looks like when we talk about a boom arm question. And the boom is the actual horizontal bar. That's what the boom is. So it's often referred to as a boom or a boom arm. Generally, the idea is that it's used to hoist something or to hold something aloft. So in the case of this particular one, we've got a string here that's connected to a higher location up here at the top. This would be the crane, this portion right there. And I've hung a weight here at the end. Now, as a problem goes in physics, there's generally about 4 or 5 things they talk about in relationship to this problem. They talk about shifting this attachment point backwards and forwards. So that's one of the questions that I talk quite a bit about. You have to be careful about the simplicity of that thought. If they just shift where this attaches, it changes the angle at the same time. Therefore, moving it isn't as simple as just changing how long the force is applied to the torque arm length. It's also changing the angle as you move it. And that's something they want you to pay attention to. So one of the questions on the test would be, how would the tension change as you move the string? And you can't merely answer that simply by saying, well, if I move the string, the torque arm is longer. No, the torque arm is longer, but the angle is smaller. So you need to be aware of both of those things happening at the same time. They'll talk about moving this up or down, same idea. That merely changes the angle though. So if they move that up or down, it's not changing the attachment point, doesn't change the torque arm length, but it does change the angle, and that makes a big difference. Of course, there's the load, which is what the thing that's hung on the boom arm is typically called. So we have loaded it by placing some kind of weight here, and they will talk about moving the load to different locations and asking how this affects the system. So what I'd like you to do is take a quick moment and draw in arrows to indicate the forces you think are acting on the boom arm in its present state. And don't be all day about it, but you're going to forget some. So take 60 seconds, and then I'll pick a couple of you to tell me what you drew. I do hope you all had a nice weekend. About 20 seconds left. All right, do me a favor, hold up the number of fingers that represents the number of arrows you just drew. Just want to see real quick, how many arrows did you draw? Okay, looking at home. All right, so I'm seeing between 3 and 4 is kind of the average consensus. So let's see. Nicole, tell me one that you drew.
One going like with the line of tension.
Okay, I think that's a good one. That's a solid one. There's got to be a force this way that's in the line of tension, sure. We'll just call this tension. I think that'd be best. Good, good, good. All right, so Savannah, what's one you drew?
Weight going downwards, so mg.
So weight for what?
The actual bar is it like straight downwards.
Okay, so did you do at the middle of the bar?
Yes.
Okay, so the weight of the bar at its middle. I think that's a good one. All right. Tyler, can you give me another one?
The weight of the load itself.
The weight of the load itself. So something like this for the load. Fantastic. And Camilla, can you give me another one? Camilla, is there any more that you can think of? Maybe Camilla has left the chat. Let's try Janessa. Janessa, can you think of another one?
A normal force.
How would you draw the normal force?
From where the weight force is.
Where this one is?
Yes.
Okay, so there's nothing actually at that point to cause a normal force. We have to look for a point of attachment. So are you thinking maybe this is where it's attached and that's what's causing that force?
Yes.
Okay, so this one is not as obvious, and I'm not trying to catch Janessa in a trap. There's actually two more forces to draw in, and they're not obvious. So I want to talk to you about the two forces that are here, and they occur at what is considered the fulcrum of our problem, which is where it's attached right here. Even though this is a statics problem, and we can choose anywhere to be our fulcrum, our problem actually has a fulcrum, a place where it's attached. And this attachment point actually causes two forces. And one of them is obvious once you think about it. There's this normal force from the wall. And I say obvious, I'm not saying that you missed it or that it is not a thing that you should have known. You've never done this before. But this is preventing the thing from sliding into the wall. So the wall is pushing it outwards to keep it in place. Think of the fact that this force has a component that's to the left. This is what's ensuring that the system stays in place. So there's that force, but there's also another force whose direction we don't know, and we have to guess. It's also from this pivot point, and it's not obvious what it's going to be, but it's a force that is either upwards or downwards from this point. And the truth is, it's kind of, if you consider this to be a teeter-totter right here at the middle, it's whether this teeter-totter is trying to pivot that point up or pivot that point down, depending on the forces in the system. And it's not an obvious force, and there's just no name for it. It's part of the force from the wall. You need to pick a direction for it, though, and just go with it in that direction. Give it a name, something that will help you identify it as a force. You might not be forced to, you may not be forced. You're probably not going to be solving for it in most cases. That's not the issue that they want to bring up in a problem like this. But it is possible that they would like you to figure this one out. So just give it a name. I tend to just call it normal in the Y direction, and this one normal in the X direction. Because what they say is that this pivot point just applies one force at an angle like so. But it's best for us in setting these problems up that we consider that there's two forces there and just guess at the direction of this one. I'm probably always going to draw it upwards. But again, not super important, not a big deal. Most of my experience with these problems is they're interested in you looking at the tension or you looking at where to put the load. So we're going to use the situation we have set up here. I hung 200 grams, and it's not quite at 100 because it was slipping off when I was making it. It is going to be, let's just put it at 97. And the bracket is at 45. I'm going to move it out a little bit so it's horizontal, though. So is that more horizontal? The string stretched over the weekend. So the bracket's at 46. All right, so that's what we got. We got the bracket at 46. And I'll write these things here. The weight's going to be at the middle, so we should put it to the middle. That's at 50. And the load is at 90, what'd I say, 8 or 7? 97 centimeters. Now, this is just a start to set this problem up, but you're going to need something else. And can somebody tell me the thing that is not given that you're going to need in order to solve for that tension? You can say it out loud, Andrew. It'll be okay.
Wait.
Well, what Andrew was going to say was the angle, and that's what I was actually looking for. I think the weight of this is still going to be 100. We're using the same meter stick as last time. So 100 grams. And this one was 200 grams. But we need this angle. I have to go measure it. So I did get a protractor to measure that angle. And sorry guys at home, I'll move the camera over in a minute. Looks like 42 degrees. So, see, I set it up right there on the table, but you'll get a better look at it in just a minute once we do the math part. So this angle is 42 degrees. Now, we're still going to do this problem like we did last week's problem, and that is we are going to do a net force and a net torque problem. I'm going to tell you from the onset, if you paid attention last week, you realized that the net torque part actually gave you your answer, and the net force one didn't. I would encourage us to start with the net torque. I think it's going to be a quicker problem this way. And if I were you, I would think of where you want to put your pivot. But remember, we place the pivot at a location that will cancel out forces. That's convenient for us. And since we're being asked to find the tension, probably the best place to put the pivot would be here to cancel out these two forces to which we don't care what their answer is. Now this gives us three torques that we have to balance. There's the torque from the tension, the torque from the weight of the meter stick, and the torque from the load. And I think from your experience last week, you guys should be able to do this. So grab your notes, think about the direction of each torque. Remember that we have a list of three of them. And if the system is static, these have to balance to be 0. And I'll give you that third little thing. Each one of these has 3 buckets. So that's all I'm going to say. You guys who are at home, I'll set you guys up into a couple of groups so you guys can talk it out. Looks like we've lost somebody. You guys in the classroom, feel free to talk to each other. I intend to hit you up for information when we're done. Don't forget to consider the direction each torque acts. There's 2 counterclockwise and, 2 clockwise and 1 counterclockwise. Those are the 3 torques that are here. But okay, I'll stop talking for a change. All right, so the first person who gets to help me out is Emma Edgeworth. Emma, can you pick any one of these and tell me about what you wrote down, please?
Okay, I'll do the torque of the 200.
Great.
For the length, I did 0.97.
Perfect.
For the force, I did 2 newtons. And then for the angle, I did the sine of 90.
Excellent. Now, did you make this positive or negative?
I made it negative.
All right, so I'm going to ask you a more probing question. Is there another one here that's also going to be negative because of that decision?
I did the torque of 100.
Okay. I figured because you set the negative sign, you have to make that. Thank you very much. Perfect. I think that's excellent. Excellent. All right. The next person who's going to help me out here is Noah.
So for tension, I did 0.46 in one bracket, and then the sine of 42 degrees, and then T as the variable.
Excellent. Thank you very much. Perfect. Perfect. And the last person that's going to help me out is, wait, they're not here. So, and I already called on that person today. So David, can you help me out with the last one?
So for the distance from the pivot point, I put 0.5. For the force, I put 1. And then for the side, I put 90 degrees.
Excellent. All right, so this is not too terrible, I don't think. They're gonna work all this out and solve this for T. I'm not gonna do that part. I don't think I have to. So is there anybody who has anything different? So I should be able to pick anybody and they'll tell me what the T is, right? So you get to spill the tea on this one. So how about Anna? Can you tell me what it was? 7.9 is what Anna got. How about anybody else get 7.9? Oh, excellent. 7.9 newtons. Sounds pretty good. Sounds pretty good. Now, I want to kind of throw something at you here. Look how much bigger the tension is from the weight that's being held. You see that, right? In fact, we look at the fact that we're holding a 2 Newton load and a 1 Newton meter stick. It's a total of 3 Newtons, but the tension in the string is much greater than that. Now, there's a lot of things about this that should make you concerned. If you're building one of these, why would you build something like this? Where if your goal is to lift something relatively small, it takes so much more force in the tension of the arm. Is that a good design from a perspective of you wanting to build one of these? You could just lift this object and it would take much less force. The boom arm does give you an advantage. I mean, if you're a crane operator, you're attempting to lift this probably over something where you can't physically fix something to lift it up. But this is a lot more force than what it is that you're lifting. What do you think is going to happen to this force as we shift the point of connection here that way? Do you think it's going to increase or decrease or stay about the same? It's a hard question. It's not obvious as to the answer. In fact, I set this up so that we could actually mess with it a little bit. So you guys at home, give me a second. I'm going to move the camera. All right. Now, here's where we're going to reach the limitations of the model over our calculation. And this is a little bit disappointing, but not terribly so. The force probe can't measure at an angle. It's just not designed that way. And although I hung out here for about a half hour on Friday, couldn't find a good way to put it at an angle. So because of that, it doesn't read the full amount of force. It only reads part of that force. And there's nothing I can do about it. So we don't really know if this is the right amount of force or not, because although we calculated about 8 newtons, it's only reading about 6, not even at 5. So as I said, there's no real easy way for me to fix that. However, I can change the angles like we talked about. I can move this thing back and forth. What I really want to do is I want to do 3 different things. And I want to talk to you about how this question would probably translate into an AP question. So first, you've done what it takes to kind of figure out what this force was. Can you look back at your work and answer questions related to what if? Here's the 3 things I think they would ask. What if this was shifted right or left? The actual load on the boom. Do you make a prediction of what you would expect to happen to the tension? You didn't solve for it this way. Remember, you solved with actual numbers. Can you look at what would happen if you shifted this further out, how it would impact what it is you just did? And at the same time, if you brought it further inwards, how would it impact what you just did? I'm imagining a thing where student 1 says this and student 2 says that. And you're having to talk about what parts of what they said seem correct and what parts don't seem correct. And as I'm making this up, I'm thinking, if I shift this in, it reduces the torque from this load. That has to be true because the torque arm got smaller. You know how these problems try to make it sound like one part might be right, one part might be wrong. The next thing I know that they'll talk about is they will talk about changing this angle. I think that one's pretty obvious. And the last one, they're going to talk about changing the connection point. Those are all the different things I know that they're going to talk about. So what we're going to do is first take a minute and just write the one answer. If I move the load in, what's going to happen to the number on the screen? The number represents the tension. If I move the load in, what's going to happen to the number on the screen? And can you predict that? Like, can you say why you think that's true? Write a sentence or something. I'm trying to kind of give you what you should expect on our next quiz or test. Somebody keep me on time, because there's no bells. So we've got, what, like 10 minutes? 5 minutes. Okay. So in your answer, did you indicate that moving the weight this way reduces the torque from the load? And that reduction in torque means that there'll be less tension in the string. And that's what you probably should say. You probably should also indicate that nothing changed about the weight of the meter stick. Identifying what stays the same and identifying what changes, we know are different points on the test. To acquire them all, we need to make sure we are being consistent. So nothing changed about the angle, nothing changed about the weight of the meter stick, but we reduced how much clockwise torque was active in the system. So I did a dramatic change in the placement of the load. Did it produce a dramatic change in the number on the screen? I think that you should be able to make that kind of prediction. I think you need to be able to talk about why it would change the way it did. Now the next one's going to be harder because what we're going to do is we're going to change the point of application, but I can't do that without also changing the angle. So what happens here is I am going to loosen this and lift the whole thing up and pull it outwards. It's going to make the angle smaller, but it's going to make the point of attachment further out. Everybody understand? That's more complicated. I'm changing two factors at once. You need to ask yourself which of these two factors is going to have the greater impact on the outcome. The angle is going to change. It's going to become smaller. But the torque arm is going to become bigger. So what are we at right now? What's it say?
4.2.
4.2? All right, so think about it for a minute. Maybe write a prediction. Again, I'm going to shift this outwards. So it's going to reduce the angle. Got 2 minutes left, so I gotta hustle. All right, so this is going to be a little bit more discombobulated. So I want to make sure I do a dramatic enough change. Is that still pretty level?
Sure.
Well, I don't know. It's level-ish. It's just so hard on me, all right?
Yeah, it's like fending.
Yeah, I know. It's starting to flex some. All right, so it didn't go out very much further, did it? Not sure how much further it went out. I can't read it from this side, so I'm at 50, almost 54 centimeters. And that angle changed to about 25 degrees. So there's a pretty big change in the angle. and not a very big change in the distance, what happened here?
Increased amount.
It's a dramatic increase, isn't it? Now, this is because the angle change causes a big change in sine. Remember, I know you don't really have a good feel for this, but small changes in angle usually produce relatively big changes in the sine, especially as the angle gets smaller. So even though the torque arm didn't change very much, this angle made a dramatic change in how much tension there is here. This is not obvious. It's not obvious in the math. It's subtle. And I'm not sure they would go this subtle in their details, but when you start changing the angle and you're dealing with the sine or the cosine of the angle, as cosine gets close to 90, you see dramatic changes because it's getting too close to 0 dramatically. Same here. Not to mention, did you notice in solving for the tension that you divided by the sine? You did see that, right? It ends up being in the denominator somewhere. That means as it approaches 0, that fraction gets bigger fast. So whenever you start messing with the sign, be prepared for dramatic changes. All right, the bell rings now. Actually, it's like 9:11, right? So I'm going to release you guys to go because we have no bells today. Technology has failed us yet again.